Okay, let's look at part 2 of chapter 13. So, in part 2, we're looking at the buoyancy force. We're also going to discuss Archimedes and the Archimedes principle and sinking and floating. Okay, so what is the buoyancy force? Well, when an object is immersed in a fluid, then there's a force that helps push it upwards. So here's a whale. This whale weighs many thousands of pounds, but he doesn't just sink to the bottom. You can see he's kind of floating there, right? So in addition to his weight, there must be some other forces. So there's the downward force of the weight, but there's also the upward force of the buoyancy force, which I'm going to label as F of B. And and those two must be very much equal to each other, or the whale wouldn't be free to swim in the water, right? So he's buoyed up by the buoyancy force. This is the same force when you've got a boat. It's being pushed upward by the buoyancy force, right? Which is opposite the weight. Now, we were talking in the last section about pressure. And yes, it is water pressure that is creating this buoyancy force. So there is greater pressure against the bottom of an object than the top of an object when it is immersed in a fluid. And so water pressure is greater as you get deeper, right? So in this case, you can see how it kind of looks like maybe this is 1 meter down, right? But the bottom is like 2 meters down at least. So the water pressure against the bottom will be twice as great as the water against the top of this object. Now, this also works even for an object that is only partially immersed in the fluid, like a boat, because the air pressure on the top is not as great. And so you have the same similar situation. There's still an upward force. Okay, and we'll be talking more about that later. Now, Archimedes' principle is that an immersed object is buoyed up by a force equal to the weight of the fluid it displaced. And again, immersed could be fully immersed, submerged, or it could be floating. Okay, so the force is equal to the weight of the fluid it displaces. So it pushes the fluid out of the way. And there's a formula down here for this. That weight is equal to mg, of course. And the mass of the object is the density of the fluid times the volume of the fluid that's displaced. And we'll talk about this formula more later, but there is a formula for the buoyancy force. Let's go look at this, a demonstration of this. So I'm taking you over to, okay, so if this doesn't pin up to be large, then look at the small picture. What I've got over here is I have 1,000 kilograms of weight hanging from this spring scale. And so the scale says that it's at 10 newtons of force, okay? Which is what you'd expect for 1 kilogram, sorry, 1,000 grams, 1 kilogram. And what I'm going to do is I've got a jar of water here, and I'm going to bring that up and immerse the fluid. And you're going to keep an eye on the scale. So I'm bringing the water up. It's now over. And you can see the scale, perhaps, it's right around 800. A little bit less than that, maybe 780. So the thing is that so 7.8. The fluid has provided an extra force upwards to buoy up that weight. All right, so gravity is pulling downward, but upward is the buoyancy force. Now, Archimedes was an amazing guy, and there are several stories about him, which I'm probably not going to tell here. Usually I do tell them in class. But Archimedes was the guy who figured out the lever, and he said he could move the world. If you had a long enough lever and a place to stand on and a fulcrum, he could lever the world up, right? So he's the one who figured out the math for the lever, which we studied in previous chapters. He invented the Archimedes screw, which is still used today to shift fluids upwards. He also created what's called the claw of Archimedes. Nobody knows exactly what it looked like. Unfortunately, there were no good contemporary drawings, but it may have been a lever with a claw that the Romans kept attacking the city of Syracuse where he lived. And so he would try to destroy their ships as they would pull up to try to attack the city, which was on the sea. And so it may have been something like this, where there was a claw that would reach down and grab the ships. Some people think that even there was a dock, and the dock had claws that would come out and attack the ships from underneath. He's also reported to have invented some sort of death ray with some mirrors, which they haven't quite figured out how he did it, but probably something more like shiny brass mirrors to make things hot. Probably was not totally very accurate, but he was such a brilliant guy, who knows. Anyway, so Archimedes, though, did figure out the story of the crown. He figured out the buoyancy force. The idea is that the king of Syracuse had a fancy crown made, and he thought that the silversmiths had done him out of some money there, that the crown wasn't made of pure gold, that it had some silver in it. And so he said, okay, can anybody figure out how to tell if this beautiful crown is pure gold or not? I don't want to destroy it, because I could just melt it down and weigh it. Then I would know if it was pure gold or not. But he wasn't sure how to do that. And so he said, I will pay people money. Anyway, so his cousin, I think Archimedes was a cousin or something of the king. Anyway, he figured it out. He was getting in his bathtub one day, and he was buoyed up by a force. And he jumped out of his bathtub and ran through the streets naked, shouting, Eureka, Eureka, which means I have found it. And so if you ever watch the TV series Eureka, they have Archimedes sitting in his bathtub. That's in reference to this story. Anyway, so he figured out the buoyancy force, and he figured out that it was the weight of the fluid displaced. Now, how did he figure out if the crown was pure gold or not? They aren't quite sure how he used the buoyancy force for that, but it may have been that what he did was he had the crown and a weight of gold on a balance. So here would be the fancy crown, and here would be some pure gold that balanced it out perfectly. And then if you put it into some water, so lowered them both into a bucket of water, well, gold is much more dense than silver. So if the crown had silver in it, then it would be taking, it would not be pushing out the same amount of water out as the same mass as the gold. So right now they're the same mass, but the volume will be different. And so what would happen was that because the pure gold, it was probably less volume, then it would push aside a smaller buoyancy force. Whereas the crown, because it has silver in it, then it would push aside a larger amount of buoyancy force because it would have a larger volume. And so because of that, this would start to tilt. So if it stayed the same, then they were both pure gold. But if they were different, then you knew that one of them had a different metal in it. So anyway, so I believe that, the conclusion was that, they had cheated the king. Okay, so buoyancy force is equal to the weight of the displaced fluid. And so to get that, since weight is mass times g, in this case, we need the mass of the fluid, right? Mass of the fluid. So I'm putting FL here for fluid. And g, of course, is usual acceleration due to gravity. But another way to get mass is think back to density. mass is density times volume. So I've got the density of the fluid times the volume of the fluid times g. And with that equation, I can figure out a buoyancy force on an object. So we're going to do an example of that. You may remember back to Pirates of the Caribbean. And there's a scene in the first Pirates where Captain Jack and Will are underneath this canoe, okay, and they walk out to a ship on the bottom of the ocean. The question is, was this just movie magic, or could this actually happen? And so there is a YouTube video of it if you want to go review. Usually in class we will watch that, but let's just do the math here. Okay, so the buoyancy force on the boat, is it greater than the weight of the boat? Let's find out. So we've got to figure out what the buoyancy force is on this boat. Now, it looks like this boat is maybe twice as long as a person, all right? So let's say it's about, since a person is about 2 meters, let's say it's about 4 meters long. Does that look about right? Yeah, that looks about right. Okay, and the other thing is that this is like a half cylinder. So let's say that this is the boat. We're going to approximate it as half of a cylinder. And it looks like that it's about halfway down their body, so that makes it about 1 meter in radius. Okay, and it's about 4 meters long. Okay, and we need this because we need to find out the volume of water that's displaced. So we need the volume of the boat to figure that out. Okay, so the formula for the volume of that boat, the volume for a cylinder is the end piece, which the area of the end piece is pi r squared. And then we multiply by the length. And then we're going to divide by 2 because we're doing a half cylinder. Okay, so anyway, so we've got pi times 1 squared times the length, which is 4. And that's over 2. So really we end up with pi times 2. Is that right? The length is 4 over 2. So pi times 2. Okay. So that's going to be around 6. So this is all an approximation. So let's just make this 6 meters cubed. Okay. All right. So now we've got a sort of volume. And let's look at the forces that are possible. We've got the 2 guys. So we've got Captain Jack and Will. And let's say that they are like, they're not the biggest guys in the world, but let's make them about 700 newtons each. And then we've got the boat, which, you know, looks kind of heavy, but they're carrying it. So maybe it's the weight of a person too. So let's make it about 600 newtons. And so altogether, that means that the weight pushing downward might be, if all of these people are, you know, they're hanging onto the boat here, that would be about 2,000 newtons. That's the force downward. Now, the force upward, of course, is the buoyancy force once they are in the water. Okay, so let's find out how big the buoyancy force is. Okay, the buoyancy force is going to be the density of fluid, which is salt water again. So density of fluid is 1025 kilograms per meter cubed. We're going to multiply by the volume, which is 6 meters cubed. And then we're going to multiply by g, which of course is just 10 meters per second squared. And so what are we going to end up with is 6,150 2, I believe. Okay, so okay, and so then what do? Well, that's the force. That's in newtons. That's the buoyancy force upwards is 61,000 newtons of force. The force downward at best is 2,000 newtons. So which one's going to win? The buoyancy force. The buoyancy force is huge. And so it is going to push that boat upwards. So it's movie magic. Even if you went back and filled the boat with anvils, it still might not hold it down to the bottom of the ocean. We use boats because the buoyancy force is so big, we can overload them like crazy. If you've ever seen a cargo ship, you know, one with all the okay, so way loaded, right? Well, we can put huge amounts of weight in a boat because the buoyancy force is magnificently large, even for this very small boat. And that's why you can load it up with lots of people and lots of equipment and it will still float. Okay, so the buoyancy force is incredibly large. So yeah, it was movie magic. And this is one reason that divers usually have to carry weights so that they will sink to the bottom of the ocean. And they can't carry a large supply of air with them because, well, there are many reasons, but yes, you can't carry a big bubble of air with you unless you've got a lot of weight to pull it downwards. Okay, so apparent weight is the weight when it's immersed in a fluid. So we were doing the example, we had 1,000 kilograms, which would be 1,000 grams, which was 10 newtons of force. But when we put it in the water, it was down to 7.8 or so newtons. Okay, so yeah, so we reduced the weight to 7.8. That would be the apparent weight when it's in the water. Okay, whereas 10 newtons would have been mg, the original weight. Okay, so the difference between those is the buoyancy force. So the buoyancy force on those weights would have been around 2.2 newtons. Okay, and you can see here we've got an example, similar thing. Here's a weight that has 3 newtons. When it goes into the water, it's down to 1 newton. The water that it displaced, this water poured out instead of merely being pushed upwards, was about 2 newtons worth of water. Okay, so all the water's still there, the weight's still there, but yeah, we've got a buoyancy force. And this is why when you go in the water, you can, you know, pick up somebody. You don't pick up people on land so much, but when you go in the water, it's very easy to pick up someone else and carry them around because of the buoyancy force. It's helping you. And it's why when you're on a rocky beach or something, you know, your feet will hurt when you're on the sand, but once you get in the water, it usually hurts less, you know, if it's pebbly, because then you've got the buoyancy force helping to lift you up so that you aren't pushing down as hard on the rocks. Okay, now the buoyancy force doesn't depend on depth, which is like really peculiar because you would think because we said it depended on pressure, then it would depend on depth. But the reason is the buoyancy force depends on the difference in the pressures between the top and the bottom of the object. And the thing is, if the object doesn't change its shape or volume, so like if it doesn't get crushed as it goes down, then what happens is that the forces on the bottom and the top are always the same difference. So you see here we've got 1 Pascal of pressure perhaps pushing downward, okay? We've got 2 upwards, 2 units of pressure. And here we've got 3 downwards and 4 upwards. So the difference between these, here, the difference was, the change in pressure was 1, right? What's the difference between 3 and 4? Same thing. The change in pressure is 1. And then it goes deeper yet. Now it's got 5 on the top, 6 on the bottom. What's the difference? Well, it's still 1. Right? So that's what provides the buoyancy forces, that difference in forces. So yes, the pressure does get greater as you go down further, but the as long as you're displacing the same volume of the fluid, then it should be the same buoyancy force. So, and also as long as the density stays the same. So actually, as you go deeper in the ocean, you might hit some areas that are saltier or more fresh. So that could change things a bit. And of course, depending on whether you're in freshwater or saltwater makes a difference. Trying to think what else I wanted to say here. Okay, all right. So let's go on and look at floating objects. So objects that are floating, that's when their forces are equal. So we started talking about the whale, and that was the thing I was just going to say about the whale. If the buoyancy force did not stay the same, then fish would have a lot of trouble swimming at the top of the tank versus the bottom of the tank, right? Their buoyancy force would be different. And so whales and dolphins and everybody else who swims down, the buoyancy force stays the same, so they don't have to worry about adjusting for it. Okay, so back to floating objects. So when things are floating, the buoyancy force must be equal to the weight of the objects, because we have to have a balance of forces for the object to be at rest. It's an equilibrium. So it's weight downward, the buoyancy force upwards. Now, we've got a canoe, and then we've got a canoe with a hippo. There's more weight, so there's got to be more buoyancy force. So you can see what happens here. The volume of fluid displaced is what is equivalent to the buoyancy force, the weight of the volume of fluid. And you can see in the second picture with the hippo, the weight of the volume of fluid has gotten greater. More has been displaced by the boat sinking down. And so that's what happens. The object sinks downward until it has displaced so much fluid that the forces are now in equilibrium. So at first gravity is winning, it sinks downward, then it reaches equilibrium, and then it has no more reason to sink any lower. Okay, so let's do a small calculation on this. So how much water must a canoe displace to float? And so I'm giving you the mass of the canoe is 30 kilograms, and the mass of the hippo is 90 kilograms. So let's find out how much water has to be displaced. So the buoyancy force equals the weight of the object. So first of all, we'll find out what is the weight of the canoe. Well, that would be mg, right? So we're going to get 30 times 10. So that's going to be 300 newtons. Okay, that's going to be the buoyancy force, and the buoyancy force is the mass of the water displaced times g, right? Because it's the weight of the water displaced. So this was the mass of the canoe, but now we want to find out the mass of the water times g. Okay, so how much water must be displaced? Well, for fresh water, or for any water. Okay, so we've got our mass of water must also, right? We must also need 300 newtons of water. I should have put. So the buoyancy force is the weight of the object. That must be equal to the weight of the canoe. And so how much are we going to need? We're going to need 30 kilograms of water times g, of course, times 10. To make that 300. So they're equal to each other, right? You can see how G would cancel out. You would need the same amount of water being displaced as the weight of the object. Okay, so what's going to happen? So that's our mass of water. If we want to find out the volume of the water, well, since mass is equal to density times volume, we can figure out how much volume of water we need also, right? Okay, but when we add the hippo, well, now what's going to happen? Well, we've figured out that actually mass of water must be equal to the mass of the canoe or the object. Now we're going to have the mass of the water must be equal to the mass of the canoe plus the hippo. So now we need 30 plus 90, or 120 kilograms of water. All right, so more water is required because there's more weight that has to be counteracted. And so for a ship, when you load it with more stuff, it sinks deeper in the water. So floating objects displace the weight of fluid equal to their own weight. So this only occurs for floating objects. Okay, what if the buoyancy force is greater than the weight? Well, what's going to happen then? Well, not the buoyancy. What if the weight is greater than the buoyancy force? We don't usually do it the other way. Okay, so anyway, so this is one reason, though, that ships can float even though they're made of iron. If you have an iron block, okay, versus having it spread out in a ship shape or a dish shape, then what happens is that the solid one can't displace enough water to equal its own weight. Why is that? Well, remember that the density of iron is around 8. So a 1-ton block of iron displaces only 1/8 of a ton of water because it's so dense. But you could spread that iron out into a bowl, and if it can displace more than 1 ton of water, then it can float. Okay, so yeah, the density of water is only 1. The density of iron is 8. Okay, so you need to spread this out to at least 8 times as much as the block so that it can float. Okay, now, so when objects are floating, it's because their weight equals the buoyancy force. When objects are sinking, it's because the weight is greater than the buoyancy force. So the block of iron sinks over here because the buoyancy force is only 1/8 of what it needs to be to float it. Okay, so sinking, the weight is greater than the buoyancy force. But if it's floating, then you know the buoyancy force and the weight, sorry, wrong one, are equal to each other. Okay, now we can also relate this to density. We were just talking about the density of water versus the density of the iron. And so in general, if the density of the object is greater than the density of fluid, then the object will sink. But again, remember, you can spread that iron out. If you can spread the iron out so that it has a large air bubble in it, then basically what you've done is reduced the effective density of the object so it can float now. Okay, so you need to get the density to be less than or equal to water for the object to float. Now, if you have objects that naturally are the same density as of the fluid, then they pretty much can be submerged anywhere in the fluid. So this is what fish achieve, right? Fish have a bladder, a swim bladder, and they can adjust their density just like a submarine can, so that they can be at any level in the water. And so whales too, they adjust their density. And just like you do when you're swimming, you can take on air, take on a breath, and then you float higher in the water. And if you let that air out, you might sink underneath the water. So yes, so you can adjust your density. When you're about equal, then you can be anywhere in the water. And human beings being 80% water, we are very close to the density of water. Okay, so anyway, so some animals can control their density. So actually alligators, eat rocks. So they load themselves down with rocks so that they're lower in the water, so that they're less obvious when they come to eat an animal. And how do they know when to stop eating rocks? I don't know. But I did read that, yeah, they have to keep eating them. They poop them out eventually. Anyway, so so they eat rocks and get lower in the water. But yes, imagine if they ate too many, then they would be trying to sink. Okay, so there's a formula here. The fraction sunk is the density of the object divided by the density of the fluid. So if you have a block that has a density that is 0.5 grams per centimeter cubed, and it's floating in fresh water, well, since the density of water is 1 and the density of the block is 0.5, then the amount that is sunk will be 0.5. So 0.5 of the block will be down in the water. Now, what if the density of the object is like 0.7? So it's still going to float because it's less than the fluid, but it's going to float lower in the water, right? It will now float where 70% of it is below the water. Okay, so it's the amount that's sunk that this formula is referring to. And so how much of an iceberg is underwater? Well, an iceberg has a density of, I think it's 908. And the density of the fluid, let's say, well, salt water. And what we're going to get is 88%, or 0.88, which would be 88% under the water. So you've probably heard there's 90% of an iceberg under the water. Well, yeah, because so you look at an iceberg like this, and to us it makes us think of styrofoam, and so we're like, okay, that's how much is under the water. But that's not true. The amount under the water is huge, right? I can't even draw it on this picture. There is around 12% out of the water and 88% under the water. Really, the iceberg has some bubbles in it too, so usually it's almost 20% out of the water. But still, it's under the water, and that's why things like the Titanic, they ran into the iceberg, and it ripped holes in their side. Okay, so anyway, so yes, so the actual iceberg is just part of the main iceberg. Okay, and so that's so the part sticking out is small. The large amount is underneath. All right, so that's the end of that. We're going to go do the last part on Pascal's principle next.